Hello. I hope that this is working. So Ada requested some division where the coefficients aren't necessarily 1. Sorry, my screen had something on it. So we're going to do this problem. We're in Z5 right now. That's important. And we're dividing 4x cubed plus 2x squared plus 8x plus 7 by 3x plus 2. What I think is really cool about this problem is I mean, we're using modular arithmetic in a way that allows us to solve something in, this ring, or I guess, is this a ring? Yeah, it's a ring that you can't do like in algebra typically. So let's set up our long division. We have 3x plus 2. 4x cubed plus 2x squared plus 8x plus 7. Yay! So you have to ask yourself, and I gotta make sure I do this right. You would normally, well, we know this is an x squared. Let's start there, right? Because x squared times this x gets me the x cubed that I want. But we need to be subtracting 4. So we want x cubed. We want 4x cubed here, right? And we want to subtract it. How do we do that? How do I make a 4x cubed? Well, we have to have a coefficient, right? Right now, I would get a 3x cubed, but that's not what I want. So, sorry, there's something on my glasses. We have to use modular arithmetic here. Normally, you would divide 4 by 3, right? And so you would say 4 over 3, and then when you multiply, that's going to get you 4, right? 4 over 3 times 3. I guess I can show that out. Cancel, you get 4. Yay! Okay. Normally you do that, but in normal algebra, that'll get you a gross thing called a fraction, and we don't want to look at fractions right now. So instead of dividing by 3, right, we're going to multiply by the reciprocal of 3, or as we're going to refer to it, as the inverse of 3. So we have to think in Z5. What is 3 inverse? Well, 2 times 3 equals 6 equals 1 mod 5. So 2 and 3 are inverses of each other. So 3 inverse equals 2. So what we have to do is multiply by 2, I think. Nope. That's not a 2. Oh, man, I messed up. 2 is the inverse. We have to multiply 4 by 2. 4 by 2, you get 8. But 8 is equivalent to 3 mod 5. So we're going to put a 3 here. 3 times 3 is 9. But 9 is equivalent to 4 mod 5, which is what we want. So it's perfect. So I hope that kind of made sense, the way I got 3x squared. And then now we'll also multiply the 3x squared and the 2. And that'll get me a 6x squared, but 6x squared is just x squared under modular arithmetic, right? 6 equals 1 mod 5, or is equivalent to 1 mod 5. Then we subtract, you get 0, and you get x squared. And you pull down the x, 8x. Okay, how do I get 3x squared to be x squared? Well, I'll need an x, right? But I need to multiply by 3 inverse again. What is 3 inverse? We said it's 2. And 2 times this 1 that's secretly here is 2. So I'm going to put a 2. And then we'll double check. We'll say, okay, this gets me 6x squared, which is secretly just x squared. And then that gets me plus 4x. And then we'll do our subtraction. These cancel, yay. And then I get 4x, perfect. Pull down the 7. How do I get the 3 away? I multiply 4 by 3 inverse. We said that's going to be 4 times 2, which is 8, which is secretly 3. So I'll do a 3. That'll get me a 9x, which is technically 4x. And then 3 times 2 is 6. They cancel, yay. It's what we want. We get 1. And so that leaves us with our remainder being plus 1 over 3x plus 2. Or this would, 1 would be r of x. This is like secretly r of x is just the 1. Whereas q of x equals 3x squared plus 2x plus 3. I hope that kind of makes sense. I think it's lovely. You just have to do some, and like, notice that this is beneficial. If I have a crazy big number, I can just simplify it by whatever mod, whatever ream we're in. 125 is a bad example. 127 is just 2 mod 5, right? Because 125 is 0, and so there's 2 extra. And it's much easier to do math with 2 than it is 127. So yeah, hope that was cool. Thank you.